everyone. Welcome to chapter number 2. My name is Dr. Max. I'm a visiting lecturer from Stuttgart University, taking over this semester a few lectures for you guys. If there are any questions afterwards, I know it's a little bit complicated these days with all the online lectures, just contact me. I'm going to share my contact details, and Rodrigo's going to do that as well. So if there are any questions, don't hesitate to contact me, and well, let's make the best out of this semester altogether, right? Today, we want to talk about the spacecraft power system, or the electronic and electrical power subsystem of the satellite. In general, we have to say that there are 5 major power generation methods. So we could tap into the solar power to generate some energy we need for our satellite by using photovoltaic or using solar dynamic methods to tap into this type of power. Another alternative would be to use fuel cells. And they could be non-regenerative. For instance, with a space shuttle, it has been used, or they could be regenerative. And, well, as to my knowledge, they have not really often flown so far, but they are still under development and are one of the future technologies to be approved. Besides the generation of power from direct sources, we also need to store the energy on board of our spacecraft. And that's why we usually use rechargeable batteries to store our energy. But besides storing, we can also use the battery as a primary source of energy as well. Just think about your normal batteries you use at home for remote control. I mean, I doubt that you use rechargeable batteries for that. So for a restricted amount of time, you still could also use just the batteries as your primary energy source on board of your satellite. Good. Well, we could tap into nuclear power. This is more like the advanced power technologies now for not so much satellites, but more for spacecrafts that go beyond our Earth system, or orbiters and missions to other planets in this kind of purpose. Things like that, we can pretty often tap into nuclear power by most of the time using radioisotope thermoelectric power. And we're also going to talk a little bit more into detail about that later. However, we could also use large-scale nuclear power plants. It's the same principle we know from Earth with rest of application. But to my knowledge, so far there were not many successful missions that rely on static or dynamic nuclear power in space. Last but not least, we have the aquatic systems, and as you can see, it's more like energy storage in that sense. We can have a flywheel, and we're also going to look a little more into detail at in a few minutes. The thing you really need to remember is, for an electrical power subsystem of a satellite, there are a lot of issues to consider. And power is one of the basic things you need on board of a satellite. Without power, well, your satellite is pretty much a zombie, not doing anything in space. I mean, there are a few missions they don't need any power, but, well, let's be honest, if you want to do some fancy stuff with our satellite and spacecraft, we need power on board the satellite. And that's why we need to consider a few more things when we think about this EAS. First of all, it's the spacecraft configuration. So, how does my satellite look like? Where can I put solar panels? Do I have space for some more advanced technologies? What about the weight? Those are really important things I need to consider even before building more satellite, just on the power level first. And then, of course, I need to know, what is the target planet? Solar panels make a lot of sense for missions around the Earth or the Moon. But think about solar panels in the vicinity of Jupiter or Uranus, or even going beyond that. There's almost no sunlight, so it doesn't make sense to use solar cells so far away from the sun. Another point to consider is the mission life. So I'm going to talk about this in a very few seconds on the next slide. That's why I'm not going to talk so much about it. But we also have to think about maneuvers. So certain type of maneuvers require more power than others. Maybe I have some really complicated maneuvers and I use an electrical propulsion system. So for this early stage, I need significantly higher power than maybe later on during my nominal mission. So I also need to consider this type with a more complicated maneuvers for my electric power subsystem. Orbital parameters are of course also very important because, especially, let's stick to the example with solar panels. I mean, it has a lot of influence how I put my solar panels aboard the satellite in relation to the sun, and maybe with the payload to my mission. So it needs to be carefully adjusted according to my orbit, that I have enough power to support my mission. And yes, the last point is payload requirements. I might have a very, well, resource-efficient bus that only requires a few watts to self-sustain, but then I have a payload like a synthetic aperture radar, where I need a lot of transmit power on board of the satellite during operations, and my electrical power system needs to provide this power whenever it's needed. So those are just some few major issues for the consideration when I design an electrical power system for my satellite. So far so good. As promised, we want to talk a little bit more in detail about the mission duration, as promised. So in this fancy plot you can see the mission duration over the power we can provide with our power subsystem. And you see right here in the lower corner, you see primary batteries. For mission duration between minutes to, well, 1 or 2 days, with a relatively low amount of power of up to 100 watts maximum. Well, whereas a mission of a few minutes doesn't make too much sense for a satellite, in my opinion, it is very much relevant for sounding rockets, for instance, or balloons, high altitude balloons. And I mean, everything that goes into space or at the edge of space is some sort of electrical power subsystem for spacecraft. So that's why it's relevant here. And if I just have a sounding rocket with a few watts of power source, I don't need solar cells or a fancy fuel cell or a radionucleic battery. I can simply stick to primary batteries, non-rechargeable. I put them in there, I use them once, and that's all. However, if I extend my mission to, let's say, a normal science mission for low Earth orbit, then we are usually in the vicinity of months to years for this mission. And usually I need maybe between 100 and 1,000 watts of power from the system. And that's why you can see why almost all LEO satellites around the Earth use solar arrays as the primary source of energy. Last but not least, you can see if we extend our mission to decades, so very long missions. You would usually, well, we still have a good choice of technologies for our power subsystem you could use. You could use the radionuclide battery or nuclear power, dynamic or static, but still the solar array is suitable for those missions. Remember Rosetta that went to by the European Space Agency, that went over to the meteoroid. They had Solari survive on solar arrays. So it didn't have a well, nuclear battery on board. Compared to maybe the NASA missions, Curiosity and so on, those rovers going to Mars, they all have the RTG on board as their primary source of energy. But well, maybe as a small background information, that's also usually related to politics and access to those chemicals you need for nuclear batteries. So since America and Russia, they have direct access to usually what is it, cobalt or plutonium. That's why they can better use it. Good. Now it's time that we talk about solar arrays in detail. When we talk about solar arrays, we usually talk about the solar panel on board of the satellite. And this solar panel is built of very much, sometimes a great number of those solar cells, all assembled on one panel. And you see a cut through of one of those arrays here, and usually you have a support structure, for instance, an aluminum honeycomb structure, and then you simply glue the solar cells on top of this structure. Well, you of course need to have an isolator so that you don't have any discharges there, but this is very much the construction of a solar panel. Last but not least, after stacking those solar cells onto your support structure, you also might want to cover it up with a protective shield. A good example here on the lower side, and the reason why we use an aluminum honeycomb structure really often is that it's really lightweight and still have a good rigidity. But most of the time, the structure is only needed for the launch of the satellite. So once those sometimes huge solar arrays, once they fold in space, well, in my opinion, the panel is not really needed anymore, at least for structure purposes. In terms of solar cells, we have a quite variety of solar cells we could use these days. Most commonly and easiest type are the classical silicon-based solar cells with an achievable efficiency of around 14%. But we could also very well use more modern solar cells like gallium arsenide or indium phosphide with 18 to 19% of a achievable efficiency, so slightly better, but still you can see those numbers are not really exciting to most of us. If we consider that only like 14 or 20% maximum can be drawn up from the solar power into our subsystem. But hey, at least it comes for free. So that's why still most of the satellites rely on solar power. However, one important thing to keep in mind is that all those solar cells usually only use a very narrow spectrum of the light. So it's really hard to find really advanced solar cells that cover the whole visible spectrum of light. Usually they only use a very small portion, and that means that you lose a lot of power in the remaining spectrum you cannot absorb in a solar cell. So that's why, especially for spacecraft, these days multi-junction solar cells are very commonly used. And with the multi-junction cell, you basically just have 3 different solar cells stacked on top of each other, and every single solar cell has a different absorption band for the light. As you can see here, after the top layer, we have first the gallium indium phosphide layer, and a diode to isolate the 2 layers from each other, so the 2 solar cells. Then there's the next solar cell, gallium indium arsenide, and after another diode, we could have a third, just like an indium solar cell top, and we just maximize our output by not wasting so much precious space on board the satellite. No? Good. Triple junction cells. Another important fact we need to keep in mind for solar arrays and solar cells is the maximum power point. So we can see here the current over the voltage in the graph, and you can see that this characteristics is far from linear. So it's highly nonlinear behavior here of the solar cell. However, in order to draw maximum power from our solar cell into our electrical subsystem, the resistance need to be almost the same within the solar cell and for the adapting system. And the point where you adjust the inner resistance of the solar cells to your low resistance is the maximum power point. You can see here on the top, the upper right block. And with the system, so you usually have some technology and some electronics. They try to adjust the current and the voltage according to your current load conditions, first of all. But also, second of all, it needs to be adjusted to temperature. Because also solar cells have a very high tendency to vary over the frequency, the different temperatures you can use. Whereas the optimum working temperature lays between 25 to 28 degrees, the temperature drop will usually cause the voltage increase, roughly by 2 millivolts per Kelvin, you can see here. So, in other words, for the same voltage, the graph gets highly shifted for different temperatures here. Also, our maximum power point shifts from one point to another and needs to be accounted for by our maximum power point tracking algorithm and technology. That being said, the optimum working temperature should lie between 25 and 28 degrees. I brought you an example from the reality, and this is a temperature plot of the flying lepton satellite in orbit. And you can see, well, you need to believe me that this is the time on this graph, but over here you can see the temperature in degrees Celsius. And you see how those 3 solar cells we have on the satellite vary from above 100, almost 120 degrees Celsius, and go down to minus 20, minus 30 degrees. So this is a very high range that our solar cells and our solar panels are under. So this is very important to remember. Usually the solar cells are the hottest, among the hottest components on board of the satellite. Why is that? Here? Well, easy to explain. First of all, they need to be enlightened by the sun. Once the sun shines on the solar panel, also the heat of the sun heats up the whole solar panel. But we also said that we only have an efficiency of about 20%, less than 20%. What's happening to the rest? What's the rest? What's those 80%? That's heat. That's heat. And that's why those solar panels are so badly affected by heat. And then on the Leo mission, we go to the eclipse phase, the Earth shadow, no more sun, just 25 Kelvin of temperature seen by the satellite of cold space, which probably really doesn't see that. Our internal heater is not on anymore. Internal heater, 20% of the solar cell, and the sun is not shining on our panel anymore. There we go. Another point to consider is radiation for the solar cells. Most of all, ionization and atomic displacement could happen due to radiation. So just think about UV, ultraviolet radiation, shining onto our protective surface we have there. Usually those are some sort of plastics or even some glass materials. If we have an atomic displacement in this layer, or some ionization on the surface, it might alter the reflective characteristics. So not all the light that comes to our solar panel might actually penetrate into our solar cell over time. but also radiation in terms of protons, trapped electrons, and other high energetic particles, galactic cosmic rays, etc., could get into our solar cell and cause atomic displacements within our gallium arsenide and our silicate. Well, this effect is really bad around the Van Allen belts, where we have a lot of those trapped high energetic particles. So the Van Allen belts are, the height between 1,300 kilometers to maybe 2,000 kilometers. And during this time, even if you want to get to a geo, you have to pass through this region. So just because you say, yeah, my satellite is a geostationary satellite of 36,000 kilometers distance to Earth, it doesn't concern me with those Van Allen belts. No, you have to pass through this region, whatever you do, and all the satellite operators find different methods how to, bring the satellite and the spacecraft safely through this region. But also for satellites that are below the Van Allen belts, this could be an issue. Because, for instance, the South Atlantic anomaly, where the Van Allen belts get really close to the Earth's surface, to around 50 to 60 kilometers above the Earth. And if you pass through this region, you have an increased level of radiation there, and those total higher dose could, over the mission time, reduce and degrade your solar cells. The short circuit current could be reduced between 6 to 12%, and the open circuit voltage around 5% after 5 years old only. And because all of that, your power system needs to be designed for the end of life, not for the beginning of life. So you're not doing yourself a favor if you just take all the fancy characteristics of a completely off-the-shelf new solar cell. No, we need to always consider the characteristics at the end of life and the degradation caused by all the different factors we were talking about. Last but not least, besides the aging of your solar cells, also physics are a simple issue there. The sun angle and the solar array current. Well, it's kind of obvious. If the sun is not shining onto your solar cell, you cannot generate or cannot get any current out of your solar cell. So that's why you see the graph there. But think about the multi-junction cells to make it more obvious. Now you not only take one solar cell, you take 3 different solar cells on top of each other. And now, it's no problem if the sun is directly shining from above, 0 degrees angle, sun angle. It just goes into layer 1, 2, and 3. And now we have a short sun angle, maybe 30 degrees. And you can already see that it's harder to get through between the different layers. And that's why you always want to have a really straight angle of your sunlight shining on the solar panel. In general, the solar power can be calculated by this formula, whereas eta S denotes the solar array efficiency we have been talking about already. C as the solar radiation constant, which is 1,358 watts per square meter for a Earth mission on average. Of course, this is only an average value because it varies a little bit over the year, over the day, and over time. But this is a very good constant you could always use as a start for your calculations. AS denotes the surface of the solar panels exposed to the sun, and LD is a light degradation factor. This is a factor that has become quite suitable to calculate the degradation of your solar cell over the years. last but not least, we have the alpha S, which is the sum incident angle which we were talking about just on the previous slide. So then by putting that all together with the shown equation up there, you can calculate the solar power. Well, but now look at this graph down here. Because all of this doesn't really include the degradation. I mean, it includes the degradation by aging, but not by all the other things we might have externally. I mean, characteristics that don't affect our internal solar cell characteristics, but how we put it together as a system layer. So we had our efficiency of the silicon cells of about 14%, and then we put it together, design assembly, you know, we have a layer, a protective layer we put on top, and then we are only 89% efficiency achieved there. Then we have a temperature variation of the array. So, you know, within the array, so not every single solar cell has the same temperature as the neighboring ones, but you might only have one maximum power point tracking algorithm for the whole array. So that's why you use another percentage there. And if you put all the solar cells in one plane next to each other, you might even shadow a little bit the cells of each other. And if you sum it up, you end up by an efficiency of only 11.7%. So that shows that solar cells are everything but efficient for our system, but still first choice for longer satellite missions. Well, just for completion here, there's some more degradation reasons you could also include in this whole analysis, but it's harder to put this one into like really an equation. But nevertheless, keep in mind that this might happen when you talk about redundancy concepts or whatsoever for your cell. So we were talking about the real life temperatures happening on board the satellite. Think about the thermal and elastic stress and tension that is caused by all those temperature variations over the mission time. So that actually might cause some tear off the solar cells and tears between the layers. We might have space debris and meteoroids just crashing into our satellite and causing a hole. It's a very interesting picture you can find on the internet with Sentinel mission from the European Space Agency, where they actually took images of their solar array at the beginning of the mission and after, I think, 1 or 2 years. And they actually were hit by a meteoroid. And they have a really nice image of a big hole in the middle of their solar panel. Check it out on the internet, it's quite interesting. And last but not least, we could have some outgassing materials that's not inside of our solar array, but might be some other components of board of the satellite. And this outgassing might put an additional layer on top of our solar cell and also cause some, absorption before the energy and the solar power enters our solar cell. So far so good. That should be to solar arrays. Please, again, if there are any questions, don't hesitate to contact me. And we would now continue with batteries and the storage, the onboard storage of energy. So, the power that comes from our solar cells can be used pretty much directly on board of the satellite by all the different components we have active. But what if we cannot use all the energy? And what if we don't have access to permanent sunlight, which is the case for most missions, even for geostationary satellites? There are a few times of the year where there is no sunlight, even those entered the eclipse. And that's why we need to store the energy for those times. And there are different ways to store energy, and this is a very neat graph, in my opinion, which shows the power density and the energy density. So the power density is a measure of how fast can you discharge, how fast can you get power out of your storage. Whereas the energy density is a measure of how much energy is stored there. And this is not the same. Remember, you might have like a capacitor. A capacitor can store, can deliver high currents in close to no time, but the amount of energy stored in the capacitor is relatively low. Now, just imagine you have a completely charged capacitor and you touch it with your finger. It might hurt, but luckily it only hurts for a few milliseconds. If you touch a socket, it also hurts, but it hurts for a long time because it has a higher energy density. There's more energy coming from the same source. And we have a lot of different things here, but usually it comes down to capacitors, different type of capacitors, even gold caps, caps that boost caps, flywheels, so some stored rotation energy we could use back into, could feed back into our electrical subsystem, or predominantly batteries and fuel cells. In general, how do batteries work? Well, I don't want to get too much into detail, but most batteries follow the same principle. You have two electrodes separated by a separator in an electrolyte. And once you put a load onto two differently cold terminals, you have a current moving from one terminal to another. And this is usually done by using either one or both of the electrodes as a source for your carriers, as a source of carriers. Critical issues for batteries is usually the depth of discharge that highly determines the life cycle of your battery. That means the higher your DOD, that implies the shorter lifetime of the battery at all. You can see a nice picture of a battery block for a satellite over there on the right-hand side. And, well, if you have this neat block of batteries, you also need to remember and always need to know that the battery is the most sensitive part of the satellite in terms of temperature. I mean, aside from your payload and requirements of some fancy, I don't know, measurements and scientific experiments you have your satellite, okay, this is a different story. But when we talk about the satellite bus itself, no other component is so demanding to stay within the temperature range than the battery. So you always need to really put a lot of effort into keeping the temperature range between -10 up to 25 degrees Celsius to provide for a long lifetime of the battery. Well, there are many different battery types. You could use nickel-cadmium, very famous, but also lithium batteries, nickel-hydrogen, many different types you could use there that come all with a different specific energy in watt-hours per kilogram over the energy density in watt-hours per liter. So they all have a different ratio between size and energy density. You can see that nothing beats the primary batteries in terms of size, weight versus energy density, but the problem is we cannot recharge them. So that's why usually you stick around this area, lithium ion batteries or nickel hydrogen in that area. As an example here, how to calculate the DOD of a nickel hydrogen battery. The DOD is usually around 40 to 60% for a LEO mission, and we can simply calculate the energy capacity by the W battery is the power multiplied by the time of the eclipse, divided by the battery efficiency, for instance around 80%, and the DOD. And as it said here, please note that the DOD can be estimated after the battery life is calculated based on the cycles your satellite is going through. So the mission time divided by the orbit time. You see the cycles. And once you have calculated that, you can actually calculate the battery mass as simply dividing your energy capacity by your battery's energy density. As shown previously in this graph, your specific energy, and we have here the nickel hydrogen battery between 50 and 100 watts per kilogram, and we put it in there. We can directly calculate the mass of the required mass of our battery. So far so good for batteries. Let's talk about other power systems. So the first example is the fuel cell power system. It's pretty much really close to the batteries we were looking at before. So again, we have an electrolyte and two different electrodes, but this time we feed more particles into our electrodes. We have oxygen being fed to the nickel electrode and hydrogen being fed onto the other nickel electrode. And instead of using our electrode itself to get our carriers, we use those materials, those oxygen and hydrogen, to react with each other and provide us with the carriers we need to have a load, put a load and a current from our different two poles. And the outcome is, well, energy and water. This system here is not regenerative because, well, we feed hydrogen and oxygen and we get on water. And then usually we'll just use the water, for instance, for, well, we could either dump it, or we use it for drinking water, or the space station, and whatsoever for the life support systems. But if we really want to have a complete regenerative fuel cell, then we need to expand it. So here we have the fuel cell, again, we have just seen. But on top of that, we have an electrolysis unit, right hand side. So we use power from the solar cells to run the electrolysis unit whenever we don't need the energy for the rest of our components. And in the electrolysis unit, we use water and split it up to oxygen and hydrogen. We could use them to store oxygen also for our life support systems, but we can almost use it for our fuel cell to feed our oxygen and feed our hydrogen from the tanks whenever we need energy to generate power. And the outcome would be water. We feed back into our electrolysis unit, and it's a closed system. But even more interesting there, this one has also some heat result that's coming out of the process. And we also can use it for our thermal management system, also for our life support. So that's why it's a really interesting concept for extraterrestrial application on board of other planets or on board of the space station. Other types of power systems could be in terms of the solar dynamic system, where we also use the solar energy, but this time we don't use a photovoltaic system, but we use the solar power to heat a working fluid and then drive a heat engine, like a Stirling engine or whatsoever. And by doing so, we have a higher thermal power efficiency and a higher power compared to photovoltaic. However, we need more components. It's a system that moves. Everything that moves in microgravity is not so attractive because of the bearings. You cannot put oil to keep the bearings smoothly running. So that's why it's a little bit troublesome. But you can reach a whole different power range. 20 to 100 kilowatts is no problem in this process. And last but not least, the radioisotope power generators or thermonuclear batteries. Those batteries, they convert nuclear power and nuclear power in terms of heat from the decaying radioactive material. Now you have a decaying radioactive material that causes heat. You can use the heat to generate power. You could use that by, again, like a system here, like to heat a working fluid, but most commonly we just use the heat directly with a thermal energy generator with different physical effects. You don't need some for doing that, and you can reach power ranges between 2 and 300 watts, and that's why it's really attractive to most extraterrestrial applications these days of non-Earth oriented probes. Usually you would use plutonium 238 or cobalt 60, and bear in mind that this is not the weapon grade plutonium. However, it's still hard to procure these days. It's nothing that you can buy off the shelf, and if you find it, it's really expensive, and that's why so far only the US and Russia have been using that to my knowledge, and they will usually it's even recycled from older missions. And there's one very famous case. I think it was the space shuttle, the Challenger, that blew off. And later on, because it had a nuclear battery on board, they found the battery on ground on the bottom of the ocean, and it has been reused on a later mission. It shows how precious those elements are. But in theory, it can also achieve large power amounts of more than 100 kilowatts. But yeah, this is then more like a traditional power generation. So far so good. So that's everything I wanted to let you know about the basic systems. So batteries and where does the energy and the power come from. And in the following, we just want to talk a little bit more about the satellite bus and the power subsystem